Hello viewers, this is Dr. Jero's channel, or you can simply call me Dr. J for short. So we are going to look at Ohm's Law. In this particular lecture, we are going to look at Ohm's Law briefly. Ohm's Law. From Ohm's Law, we are going to look at just the definition of resistance and resistivity. We'll also look at definition of potential difference. Look at definition of potential difference. Abbreviated PD for short. After which we'll just breeze through. We'll look at resistors in series and in parallel, or simply combination of resistors, where resistors are either in series or in parallel. So these are going to be the focus on this particular lecture. So first and foremost, let's look at Ohm's Law. Ohm's Law. Ohm's Law gives you a relationship about the current flowing in a conductor, the resistance, and the potential. So Ohm's Law is simply stated as, Ohm's Law states that the potential difference across a metallic conductor, we can write that the potential difference, let's use the short form, the potential difference across a metallic conductor is directly proportional to the current flowing through it that is flowing through the conductor, provided temperature and other physical factors are kept constant. So that is Ohm's Law for you. That law can be expressed with an equation where we say that the potential across a metallic conductor is directly proportional to the current flowing through it, provided temperature and other physical factors are kept constant. So V is proportional to I. We can call that, let's just label it equation 1 if you want to. So we can then write that V over I is equal to R. So, or we can simply say V is equal to IR. So this equation expresses Ohm's Law. In the above equation, R is the resistance of the material. We'll come to that later. Now, we need to note that Ohm's Law can only hold for atomic materials. Ohm's Law is only valid for atomic materials. Ohm's law is not valid. Ohm's law is not valid for transistors, electronic diodes, and tungsten wires. So like I said, Ohm's law is valid for only atomic materials, but is not valid for electronic diodes, transistors, and tungsten wires. So based on that, we can now go further to explain or to categorize materials that obey Ohm's law and materials that do not obey Ohm's law. Let us categorize them now. Materials that obey Ohm's law are referred to as ohmic materials. They are called ohmic materials. Materials that do not obey Ohm's law are called non-ohmic materials. So materials that do not obey Ohm's law, we refer to them as non-ohmic materials. Giving you some examples before. Those are electronic diodes, transistors, tungsten wires. Some other examples of non-ohmic materials. Hydrogen tetraoxosulfate 6. We have neon gas. We have, okay, I've mentioned diodes before. So these are non-ohmic materials. And for non-ohmic materials, the current voltage relationship is a curve. For non-ohmic materials, the current voltage relationship, just say IV, the IV current voltage relationship is a curve. Current voltage relationship is a curve. Why for ohmic conductors, the current voltage relationship is a straight line. When you plot it on a graph, it gives you a straight line through the origin. Something like this. This is for ohmic. For non-ohmic, you have something like this. You can have something like this. This is non-ohmic. This is ohmic. So next we are going to look at resistors, or resistance. First of all, resistance and resistivity. That's what we are going to focus on now. Resistance and resistivity. So let me wipe this. Let me take this off. So let us look at resistance. Resistance is simply the opposition to current flow in a material. That is resistance, the opposition to current flow in a conductor. Of course, recall that Ohm's law, the equation representing Ohm's law is that V is equal to IR. So from that equation, we can get an expression for resistance as what? V over I. So we can also define resistance as the ratio of the potential difference to the current flowing through a conductor. Then the resistivity of a material, resistivity. The resistivity of a material is defined as the resistance offered by a cross-sectional area of the wire per unit length. Resistance offered by a cross-sectional area of the material per unit length. So from that expression and from that definition, we can write an expression for the resistivity of a material. Resistivity is the resistance offered by a cross-sectional area of the wire per unit length. So our resistivity is resistance times area over length. We can, from that expression, we can get another expression for the resistance of a material where we can say R, which is the resistance, is equal to the resistivity times the length all over what? The area. So from that equation, we can see that resistance depends on the resistivity, or we can just simply say resistance is directly proportional to what? Resistivity. Resistance is also directly proportional to the length. Resistance is inversely proportional to the area. So we can say that the resistance of a material depends on some factors. Number one, the length of the material, the cross-sectional area of the material, the resistivity of the material. The resistance also depends, arrow also depends on the nature of the material. R also depends on the nature of the material, and it also depends on the temperature of the material. So I'm going to wipe this off. We can define the resistance, we can define the resistivity of a material by, or in terms of the conductivity of the material, where the resistivity is expressed as the reciprocal of the conductivity. In the same way, the conductivity can be expressed as the reciprocal of the resistivity of the material. So that takes us to potential difference. Potential difference. In my previous lecture, we talked about current, whereby current is seen as the movement of charges within a conductor. So for current to flow, there must be movement of charges, and those charges we refer to them as mobile charge carriers. So here we want to see the relationship between the movement of those charges and the voltage. So we define the potential difference between any 2 points as the work that is done when a coulomb of charge moves from one point to another in a circuit. So we say PD is the work done when a coulomb of charge moves from one point to another in a circuit. So we can say mathematically that V is equal to W over what? Q, where W is the work done, Q is the charge, V is the potential difference. So that will take us to combination of resistors. Combination of resistors. So I'm going to wipe what is on your screen so that we can look at combination of resistors. Combination of resistors. Resistors can be combined either in series or in parallel. Either in series or in parallel. When you have resistors connected in series, we can express that in the figure below. Assuming we have two resistors, R1 and R2, let's use this to represent one. Let's call this one arrow 2, call this one arrow 1. This is negative terminal, this is a positive terminal. Now, when you have a situation where when resistors are connected, such that their common point is not connected to another circuit, then we say that the connection is in series. We say that they are connected in series. Now, if you check this particular example, this is their common point. That is the point between the two resistors. You can see it is not connected to another section. It is just single between them, no connection to another section. So when you have resistors connected like this, you say that they are in series. And when resistors are in series, the same current will flow through them. The same current will flow through them, but they will be maintained at different potential difference. The only way they can have the same value for potential difference is if the resistors are equal, that is, they are having the same value. But take note that for resistors in series, the current flowing through is the same, but the voltage is not the same. And so if you want to find the effective resistance of a material in series, you have to use the summation law, so that the total resistance is arrow 1 plus arrow 2 and so on and so forth. That equation can be derived, but we'll have to do that maybe in one of my subsequent lectures. Then let us look at resistors in parallel. Resistors in parallel. Now, if you have a connection of this sort, this is a point, this is the negative terminal, this is the positive terminal. Current is coming out from the cell. Let's call this one I2. This is arrow 2. This is arrow 1, I1. Now, for resistors in parallel, they are maintained at the same voltage. Current is not the same. But voltage is the same. So for resistors in parallel, different current flow through. Why? When this current moves from the cell down to this point, it will split into two parts. One coming through arrow 2 and the other going through arrow 1. This point, we refer to it as a node or a junction. So in a circuit, a point where current can split, is called a node or a junction. It's called a node or a junction. So for resistors in parallel, The equivalent resistance is given by the reciprocal law. So if we have a parallel combination of resistors, we can say effective resistance or the total resistance is obtained using the reciprocal law. This can be extended to 3 or more resistors in parallel. Then there is a point you need to note that in wiring of your houses, the appliances are connected in parallel. They are not connected in series. The reason you connect in parallel is to allow each device to operate independently of the others. So that when you switch off one device off, if you switch off one device, it will not affect the other one. Remember, when components are connected in series, you have the same current flowing through them. So if you switch off one component, it automatically affects the other components. But when you connect them in parallel, they can operate independently such that if you switch off your fan, it will not affect your television. If you switch off your television, it doesn't affect your fan or your bulb light. So that is why, in terms of household wiring, the components are connected in parallel so that they can operate independently. So in our next lecture, we'll consider some examples, parallel combination of resistors and series. Solve some examples, then before we proceed to other aspects of this lecture series. Once again, I'm Dr. Jero. I love teaching physics. I love physics, and I try to bring physics to you in a very concise and easy manner. So do well to like my channel, subscribe to my channel. You can even suggest modes of making this lecture more improved. Thank you.